Testing for sound. We're good. Okay. So over the last little while, we've been talking about chemistry and what is chemistry, right? And the chemistry is all about how stuff changes, but I don't actually need to use the word stuff. The word is matter. How does matter change, right? And so we've been talking about some changes you might see, things like qualitative changes, quantitative changes, physical changes, chemical changes. But we've also been talking a lot about like, well, what is this stuff? How do we define it, right? And the word we use instead is called matter, right? And I think that we've seen flow charts before that kind of describe how we describe our stuff. There's elements. I'll put that over here. There's elements. There's compounds. There's also mixtures. Those are kind of our main categories. And hopefully you're getting more and more comfortable with naming elements and finding elements. Because really that's the same as this thing right here. If I give you 70 and 120 with an unknown thing right here, hopefully you can figure out who that is even. How do I know what to call this thing if there's 70 down here in the corner? Well, just find your periodic table and figure out who number 70 is. Who's number 70? Let's look it up. 70. YB. Boy, that's one of the rare ones, isn't it? What's YB? Tibium or something like that? Anyways. Right, so if I want to figure out who an element is, we need to know this number down here. What's it called again, that number? What's the name for it? Oh, I heard it. Someone say it louder. Yeah, this is the atomic number. And it literally tells you, like, who an element happens to be. This number up here in the top corner is called the mass number. NUMBER. And it tells you basically how heavy the nucleus is. So if you have 70 protons, because this is a proton right here, then this is protons plus neutrons. So earlier today, even I kind of said, like, there's got to be 50 neutrons, right? Because 70 protons plus 50 neutrons would give you 120 total, we call them nucleons, I guess. You ever heard that word before? So anyways, I'm kind of getting off topic here because that's the previous stuff we've learned. But you get what I'm saying here? If that's still a struggle, can we talk? Can we work on that? Because we got to get that building block filled in. Currently, we're now going to work on the next kind of section here, which is compounds. And we, last day on Friday or Thursday, whenever it was, we talked about how to name certain compounds. We talked about how to name things that are either covalent and molecular or things that are ionic. Okay. And so before I go on in my notes here, I want to do a little bit of a review. I mean, I know my next slide even discusses this, but let's review the difference between ionic and covalent, as well as maybe an example on how to name them. Okay. An ionic bond would be best shown using one of these Bohr diagrams. These Bohr diagrams are really good for being able to illustrate things because we can see the electrons in their different like rings or orbitals or energy levels, and we can see whether the energy levels are either empty or full, because really that's what's ideal. Either it's empty or full. This one right here used to have one electron sitting right here. It's got like one too many. And this one right here, I know I didn't put them in groups at 2, but it needed one electron. It's almost full, right? So if someone literally gives its electron from one to the next spot here, and there is a transfer, we call that ionic. And the reason why is that they were ions. This guy right here became a cation because it lost an electron and became positive. And this one right here became an anion because it gained an electron to become negative. And put these ions together, ionic bond. Now, how do you name an ionic bond? Very straightforward. All you do is you name the first word, which is always the cation, and then you name the second word, which is always the anion, except you change the ending to IDE. That's it. Let's do like a pretend made-up example. Let's say that this was magnesium, and this was chlorine, hypothetically. I know that's not actually how the electrons would work on that one, but let's just pretend. How would you name it? Well, you'd say it's magnesium chloride. There you go. Or let's say that this was sodium and oxygen. You would call it sodium oxide. That's it. One of the things we may need to do in terms of writing out the formulas, remember those little like little manipulatives I had, like that looked like, say, like this one here, or like this one here, we tried to like see how they fit together. They're over on that side wall over there. Right? Sometimes we have to look at those to make sure the charges fit each other, but that's ionic compounds. On the other side of things, then there's your covalent, or sometimes we call these things molecular compounds. And molecular compounds have molecular bonds. And the difference between these guys right here is that rather than having like a transfer of electrons, they share. And the best analogy I've ever found, maybe you're sick of this one, is like, say you're going to the cafeteria. Okay. Hypothetically, you want to buy something that, I'll just go with a nice round number, is $5. Okay. I happen to bring $6, my friend has $4. And what I'm looking to buy is $5. Well, if I have $6, I have an extra dollar, right? I could then give my excess money to my buddy, and now he can be like picked up in a way. Which of the two scenarios is that one? The ionic or the covalent? Yeah, it's the ionic, because here someone has an extra dollar, and here somebody needs one, right? And so I just literally, here, go ahead, you have it. And now my wallet's empty because I've given away my excess. So just like this ring is now empty. And my buddy, his is now full, I guess, because I gave him my extra one. Although I guess in a way he's going to go spend that money. Whereas here's the other scenario. Okay. I want to go buy something in the cafeteria for $5. I only had $2. My friend only had $3. What do we have to do in order to buy whatever it is we want to buy? We want to buy, I don't know, burger and fries, right? If I have 2, he has 3. We have to pool our resources. We have to share them. But like, did I have extra and he had not enough? Well, that's not really how that works. You get what I'm saying there? But by like pooling your resources, I'll even write that on here. Pooling, ooh, that's not how you spell pool. Yeah, let's try again. Pooling resources. What ends up happening is this bond occurs because there's some electrons that are kind of in the middle. If you can kind of visualize this picture, this guy right here has 1, 2, 3, 4, 5, 6 electrons that are just his. And then 2 that are kind of like in the middle that it has access to. So it's got 7 and 8 there. And this guy here has 1, 2, 3, 4, 5, 6 electrons that are just his. But there's 2 that are like in the middle. It's like in the community pot that like anyone has access to. And that's how it fits the octet rule. So that's the molecular ones. Now, when it comes to naming molecular compounds, one big difference is that you don't have cations and anions. You don't actually ever have cations. You only ever have 2 negatively charged items. They're both negatives. They're both always anions. And the big difference here is that although you still end it in the word "ide," you have like a prefix that you put in front of it, like di or tri or tetra. And so, for example, if we have CO2, you guys know this one, right? We call it carbon dioxide because of the 2 oxygens. If I give you N2O5, it would be di-nitrogen pentaoxide. Does that make sense? If it doesn't, because I mean, I'm giving you like a 5-minute recap, right? Like this is like previously on Science 10, right? Like here's the 5-minute recap at the beginning of the episode. Okay, if that doesn't make sense, make sure we talk, okay? Because I do need to move on. Okay. Here's one more picture kind of describing the concept again of covalent versus ionic bonds, sharing versus transferring. But I want to move ahead to some of like the weird anomalies. That's what today's lesson is about. And there's 2 kind of things that we need to like upgrade to. And you probably didn't learn about this in Science 9, although maybe you did. I don't know. It depends on what your teacher taught. Because this is kind of like the real tail end of Science 9 curriculum. There are some elements that have more than one charge. You guys see that on your periodic table at some point? I think even one of our quiz questions was about like iron, I think it was, and I wanted to know which was the most common charge. Like, for example, can you guys find chromium on your data booklets if you have a data booklet nearby? Look for chromium. Chromium is number 24. And so the square for chromium, when you find it, it'll have a 24. Where does it put this one? In the top corner here? And it'll put chromium right there. And hopefully, I'm going to look off Isaiah's real quick here. Where do they put them this time? Okay, so they put them right about there. There's a 52.00 right there. I don't care about that yet. And I think it went 3 plus and 2 plus. Can you guys find that on your tables? This is known as something called multivalent, if you haven't ever heard that word before, where it has more than one valence electron possibility. This thing can either lose 2 electrons or lose 3. And everything that's like in the middle of the periodic table, we call those the transition elements. They sometimes have more than one charge. Sometimes they have more than 2. My favorite one is letter W. It's called tungsten, if you guys can find W. Maybe your periodic table doesn't even list it, but it has at least 6 known charges. +2, +3, +4, +6, and +7. And so like it's weird how some of these things work. Long story short, if it can make more than one ion, that kind of screws things up for us. Okay? Because it means that we can combine things in more than one way. We could either use the 2 ion or the 3 ion when making our compounds, and we need to know which one it is. Okay? Because they are different from each other. So I want to start off with this example. What will we call a Cr2s3? And so here's how this might look. I would start by saying, well, Cr2, well, that's chromium, right? So I would name it as chromium. And S means sulfur. We would change the ending of that to sulfide. Here's the problem. Although this is chromium sulfide, this compound here is also chromium sulfide. And they are very different from each other. They are both chromium sulfides. But they use different charges. One of these two compounds used the 3 version, the 3+ charge, and one of them used the 2+ charge. And we need a way to differentiate. And so what we do is we put in between the two words a Roman numeral. You guys know your Roman numerals? Like this is a 1, like an I is a 1, right? 2 I's is 2, 3 I's is 3. Anybody know what 4 is? Yeah. And so the reason why that works is that V is the Roman numeral for 5, and this means 1 before 5. So what is one number before 5? 4. Okay. And then like this would be 6, if you get that far. VII would be 7. VIII is 8. And then we don't actually have one that works that same way for 9, because we hop to 10, which is X. And so 1 before 10, which is 9, would be IX. So if you've never seen Roman numerals like that before, I can give you a quick tutorial. Honestly, you're not going to need to use the crazy ones. Like, we're usually talking 2 or 3 or maybe 4 are our charges. So in this little location here, we need to put a Roman numeral of either 2 or 3, because 2 and 3 are the charges for chromium. Which one's more common, by the way? How do you know which one's the most common? Yeah, the first one. Yeah, the one that's listed first is actually the most common. So if we're unsure, 3+ happens the most, because your table only lists some charges. I happen to know that chromium also has a 6 charge that's possible. It's very rare, but that's one of the problems with periodic tables, is that all these weird exceptions, sometimes you need to like have a really thorough table if you want to have them all. So, anyways, let me go back to this one right here. As I look at this, I got to figure out whether it's the 3 version or the 2 version. And so I'm going to kind of draw out those little manipulatives, just because I want you guys to be able to see this again later. So chromium either is a 2+, and I think I drew my 2 pluses like this. So this would have been a plus here, that was right like this. Either chromium is a 2+, or chromium is a 3+. So a 3+ would have looked like this. 1, 2, 3. Those are my choices for chromium. What about sulfur, though? What is sulfur's charge? Well, sulfur's charge is -2. So I'm going to try drawing it with the 2+ version. Here's a -2. And if I kind of filled this in right here, this would have been the one that fits the -2. You would need one of each of them, right? If you had one 2+ and one -2, wouldn't that be this one right here? So this guy would be chromium with the 2 version. But if we're looking for this one up here, this would be one of those ones where I'm going to have to draw quite a few of them. I'm going to need to have like a 2-1 sitting here, a second 2-1 sitting there, a third 2-1 sitting here, and I need like this one kind of filling in the gaps. Plus, plus, plus. Does that kind of make sense, my visual there? I mean, I can go grab the actual manipulatives. But here, look, I have 1, 2 of my chromiums, and 1, 2, 3 of my sulfurs. Does that make sense that this must be the chromium 3 version I'm using? So my Roman numeral I'd put in the spot right here is chromium 3 sulfide. And it helps indicate to me which of these possible charges was being used. Did any of you guys ever learn this before? Did you get that far in Science 9, or is this new now? I'm saying new. Okay. Okay, so I'm going to spend a little more time on this then. I'm going to try another example here. Let's talk about iron and oxygen. Let's talk about some compounds I can make with iron and oxygen. What is iron's possible charges? Plus 2 is one of them, right? And I think iron can also be a plus 3. You guys find that? What is oxygen's possible charge? Okay, minus 2. Okay, so let's talk about this compound here. What if iron 2 plus tried to fit together with iron 2 negative? Right? Okay, 2 pluses, 2 negatives, they just fit together perfectly, right? So I could make a compound between these two, which would be FeO. And they would just slot together just dandy. Never hear that word enough, dandy, right? What would we name this, though? Well, we'd call this iron, we'd call it oxide, but because I used the 2 plus version right here, we would call it iron Roman numeral 2 oxide. And that's one possible iron and oxygen combination. But there's actually more. There's actually an alternate one that can happen. Let's say that it was iron 3 plus that reacted, because maybe iron loses 3 electrons. Okay. Here, actually, maybe I will go grab my manipulatives for this one, just because if this was slightly new to you guys. Let's go grab these again. We need the 3 pluses and the 2 minuses. So 3 plus, 2 minus. Okay. So here's an iron 3 plus, right? And here's an oxygen 2 negative. Do those guys fit together? No, they don't fit, right? Okay, so add another one of these ones. Ah, shoot, negative's too big. Okay, another one of these ones. Ah, now positive's too big. Ah, there we go. Now it fits, right? Right? And if you guys need to like draw something out like that, feel free, right? So now we've got to consider, well, how many of each do we need to make it fit? Well, we needed 2 of these and 3 of these, right? So as I go back now and I write this out, right, I'll even do a quick diagram on here. We needed a 1, 2, 3 of this with a 2 of that. Well, that didn't fit. So I added another one of these guys. Oh, now it's too big the other way. Okay, well, do another one of these ones. Oh, now too many positives. Right, like a diagram like that, if you don't like instinctively see it, might help. So how do I name this thing now? Well, first I need to say how many there were. Fe, how many irons did I have? I used 2 of them. 1, 2. How many oxygens did I use? 3. 1, 2, 3. So we'd call it Fe2O3. These 2 compounds here, this one and this one here, they are different. They have different chemical properties. They have different physical properties. They'll have different boiling points, different colors. One might be malleable, one might not be. Right? Like everything could be different between them. They could be similar. But these guys need different names then. So if this one was iron 2 oxide, we're now going to call this iron 3 oxide. And this is where I find students start to struggle, is they look at this 3 right here, and they say, but Chris, this number right here was a 2. Let me say that one more time. They'll say, Chris, this number right here was a 2. Why did you call it iron 3 oxide? But this 3 wasn't based on how many you had. It was based on which charge version you used. So that becomes a little bit tricky. You got to make sure you're really clear on that. And so now we have this compound with this name and a different iron oxide compound with a different name. Yeah. Exactly, yeah. So whichever charge you use, that's the Roman numeral. Let me do another example. This is important, and if you haven't seen this before, I don't want to short this section, so let's try another one. I just got to think of one off the top of my head here. Let's try lead, which is lead, Pb, and let's try chlorine. Let's try to add some leads and some chlorines together. So first thing I need you guys to do is tell me what sort of charges lead is capable of having. Can you find lead on your periodic table, Pb? Tell me what charges it can have. What was that? Okay, so it looks like lead can have a +2 charge, or lead can have a +4 charge. What about chlorine? What sort of charge does chlorine have? -1? Okay. Right, so that thing just fell. Let's see how these things would fit together. This guy right here, you'd have one of these where there's like 2 positives to it. And this guy would just be a single negative. Well, that's not going to fit, right? But hopefully you can kind of see how this would work. Well, what if I just use 2 of those? Okay, so that means you need 1 lead you need 2 chlorines. But how do I name this? We call it lead, Roman numeral 2, usually in brackets. Doesn't have to be, though. And then chloride. Again, some kids, they say, well, why is it the number 2? They say, this lead right here didn't have 2 afterwards. Well, it's not about this lead having the 2. It's about it being that charge that we used. That is one possible lead and chlorine combination. However, there's actually a second one. What about lead 4 and chlorine? Well, here, I mean, I don't even have a manipulative for a 4 because they're so rare. You'd have 4 of these. Well, hopefully you can kind of visualize. Wouldn't you need to have 4 individuals of chlorine to make it work? That would be PbCl4. You have 1 lead and 4 of these chlorines. We would then name that lead 4 chloride. And these 2 compounds could be very different from each other. They could be really similar, but they also could be like entirely different. One could be red, one could be blue, one could be solid, one could be gas. Well, probably not gas. One could be solid, one could be liquid. One could be, brittle, one could be really firm. I don't know. Or they could be all really similar. So that's one of the unique twists that I need you guys to be able to kind of work on. And I've got examples later, so maybe I'll move ahead and we'll come back to some examples in a bit. But that's one of the twists that kind of makes chemistry a little bit more challenging is, well, what if there's more than one charge? The second twist is something known as a polyatomic. And there are certain chemicals where it's not binary. Okay. I'm going to flip back to my very, very first slide. You guys stay here, though, okay? I'm going to go back to my first slide. When I taught you guys last day ionic compounds, I taught you guys how to do something called binary compounds. Bi, the prefix meaning 2, basically, 2 of something, where there's only 1 calcium and 1 fluorine. Well, okay, maybe there's 2 fluorines, but like there's 2 different things. There are some possibilities, though, like for example this one where there's Na, there's O, and there's H. Or there's N, and there's H, and there's C, and there's O. You see how there's like lots of different elements all shoved together? We call those polyatomic because now it's more than just 2. Now it's 3 or 4 or 5 or 6. Okay? And so that's what I want to talk about in this branch right here, the idea of what happens if there's like not just 2 things, it's not just binary. Okay? So we call these things polyatomics. And what ends up happening is the entire section of atoms works as like a conglomerate, like it's all one big section. For example, one of the known ones we have is called NH4+. It's called ammonium. And what ends up happening is there's 1 nitrogen and 4 hydrogens, so 5 atoms all squished together, and collectively they have a plus charge to them. And so in a way, this acts just like an element, only rather than there being just 1 thing inside there, there's actually 5. And we can find these polyatomics. If you guys have your periodic tables nearby, you know how like your periodic table has like this sort of shape to it where there's kind of like a little bit of a gap kind of in the middle here? There's a little chart inside there, and it lists a lot of common polyatomics. So if you're not sure what to name them, look for a little chart in the middle of your periodic table there. Okay. Let me try an example here. This one right here, MgSO4. You might freak out going, holy smokes, hang on, there's an Mg, there's an S, and there's an O. That's 3 things. As soon as you see that there's more than just 2 things, it's more than binary, it means something has to be polyatomic. And so you got to figure out where the break is. And the break goes right here, because we know that Mg is a 2+, right? Mg right here is a 2+. Well, that means we need to figure out what the heck we call an SO4. So if you guys have that table in front of you, can you see somewhere on there something called a sulfate? S-U-L-P-H-A-T-E, or maybe F-A-T-E. See that? SO4, 2 negative. It could be with an F, by the way. You can spell sulfur with either an F or a PH. Both are considered fine. Well, the way this works then is that the entire SO4 has a 2 negative charge, and magnesium has a 2 plus charge. Fit them together, now you've got magnesium sulfate. Or here's another one, barium and carbonate. Barium is Ba with a 2+. Well, that means that CO3 must be like some sort of polyatomic. And if you can find it on your table, CO3 is called a carbonate. A lot of these things are an element mixed with an oxygen somewhere. And it has a 2 negative charge, so bring them together, and you have barium carbonate. But there's actually 3 atoms there. There's 1, 2, 3 there. One of the things that we did in our activity the other day is we used baking soda. And baking soda has this formula, NaHCO3. It actually has 4 elements all shoved together. There's a sodium, a hydrogen, a carbon, and 3 oxygens. Can you guys try to figure out what we actually should name baking soda? Na. We know what Na is called, right? That's called sodium. Is there an HCO3 listed somewhere on that table there? What was it called? Did it list it as a hydrogen carbonate or a bicarbonate? HCO3, not just CO3, but HCO3. Is it listed on that particular table? HCO3. Hydrogen carbonate, there it is. Yeah, it's about the maybe 7th one down on the list, HCO3. And so if CO3 is a carbonate, HCO3 is known as a hydrogen carbonate. Move that out of the way. Onate. Now, the thing about naming polyatomics, you never change the endings anymore. Okay. You know how we always change the endings to like "ide"? Like barium chloride, barium sulfide, barium oxide. We never change the ending. So this actually is easier now. You don't even have to worry about changing this to like IDE. That doesn't even happen on polyatomics. You literally just name what you see here, and you just have to look this guy up on a table. So this one, look up on table. So now I've shown you 2 new naming schemes that we can add to our list of how to name things. We've got our covalent and molecular type things, where you use like di and tri. We've got good old just regular binary ones, where all you do is you just change the naming to ide. But now we need to add on things that are multivalent, where you put like a Roman numeral charge right here, or polyatomics, where you have like more than 2 different elements shoved together. Polyatomics are fairly easy though. All you do is you name the first one as you see it, and the second one, you're probably looking it up on a chart. Don't even change its name. Okay, we need to practice now. So I've got some practice examples here. So let's try some of them together as a group. The first thing you're going to want to do is try to figure out what type of compound are we talking about. Is it ionic? Is it covalent? And if it is ionic, is it like a simple one or a more complicated one we just learned about? And right off the bat, as I look at this first one right here, I see 3 different letters. I see an Na, I see a Cl, and I see an O. 4 of them, in fact. This must mean it's polyatomic. So if it's polyatomic, I need to go find that little chart at the top here, and I've got to figure out how to break this thing in pieces. I'm going to break it right here. Na, because Na, sodium's a metal, right? So I'm going to call this a sodium. You just got to look up, what the heck is a ClO4? Search that table. Can you find ClO4 in there? There it is. It's called a perchlorate. It's about maybe the 8th one down, if you couldn't find it. ClO4 is called a perchlorate. And that's it. Like, that's all there is to it. We don't need a Roman numeral this time. We don't need to change any endings. We don't need any dies or tris. If it's polyatomic, you just name it as you see it. Let's find the next one. Again, same concept here. There's an Sr, an S, and an O4. I'm going to break it up like this. Sr, I know that one. That is strontium. What the heck is an SO4? Okay, well, back to your table. Dig through your table and try to find out what an SO4 is. What was it? Sulfate, yeah. S-U-L, I'll use PH for spelling it, but you could use an F, by the way. Sulfate. Strontium, sulfate. There you go. Okay, well, this next one's a little bit more challenging. There are brackets in this. Like, you see this bracket sitting right here? What the heck's up with that? Well, I want to try to explain the reason why there's a bracket sitting inside here. If we look up the charges quickly, a Ca has a +2 charge. That's calcium. Can anybody find an NO3 sitting in that table? There, ignore the 2 on the outside here, but just this NO3 right here. It's called a nitrate. NO3 is called a nitrate. But look, its charge is 1 negative. Do these things fit together perfectly with a +2 and a -1? Well, no, they don't. So what I would need to do is I would need to have 2 of these. But here's the problem. If I named it like this, Ca, I need 1 of them, and NO3, I need 2 of them, you know what it looks like now? Now it looks like I need 32 oxygens, right? Because I said I needed NO3 twice. So what we do to like separate it so that it's clear is we put the NO3, that whole polyatomic thing, in a bracket, so this 2 means we have 2 of all of it. Okay? If I wanted to draw it kind of differently, it might look like this. I'll have to erase this later for space, but it might look like CaNO3 with a second NO3. Like, that would be really cumbersome to write that, but really what we've got is 1 calcium, 2 nitrogens, and 6 oxygens. Can I say that again? There's 1 calcium, there's 2 different nitrogens, and there's 1, 2, 3, 4, 5, 6 oxygens in this compound. But like, since this is kind of awkward to write that way, we'll write it with brackets. Anyways, let's name this thing then. Ca is calcium, and NO3 was nitrate. There we go, we're done. Let's try the next one. There is N, there is H, and there is Cl. Now, this is a weird one. This kind of takes a little bit of practice to get used to like knowing where to cut it in half. But there's no metals here actually. There's no calcium, or there's no strontium, there's no sodium. All of these were nonmetals. It actually happens that this one right here got cut in half right there. Probably the very, very first thing on that list of tables is something called an ammonium. Can you guys find that one there? NH4+. Ammonium. NH4+ was called ammonium. And then Cl is called chlorine. This would be the one time where you actually do have to make one change, though. We'd have to call it chlor. You'd still change it to ide. If the second thing is ever like a non-metal, oh, and ended in ide again. Okay. But like if this word is a perchlorate or a sulfate or a nitrate, don't change these endings. But since this was just a single chlorine, then you can end it in ide again. It's kind of a weird exception to the rules. That's why I threw this one on here. Let's try the last one. What does Cr stand for? Okay, so this is chromium. And I think we looked up CO3 earlier today, didn't we? Wasn't CO3 called a carbonate? That's chromium carbonate. But wait, hang on a sec here. We're putting everything we learned together today. We learned that earlier today CO3 was called a carbonate, but we also learned that chromium has 2 possible charges. Remember how chromium could either be +2 or +3? We need to combine things. We need a Roman numeral here, 2. Not only did we use this crazy 3-molecule thing here, or like 2 molecules, like the polyatomic, but if we used chromium has more than 1 charge, we need to put a Roman numeral here. So let's work backwards. Chromium can either be 2 or 3, because that's what we learned earlier today, right? Or 6, by the way, but it's 2 or 3. What was carbonate's charge? What's the charge on a carbonate? Can you find that in your table? It's -2. Okay, so let's talk this through. If carbonate has a -2 charge and you have 1 of them, what charge would chromium need to be so they just fit together just perfectly? It must be the +2, right? So now I know which chromium to use. It was chromium 2 carbonate. Because if I use the chromium 3 version, hypothetically, let's say this was +3 and -2, would they have fit together so nicely? Nah. We would have needed to like use a certain number of these in the corner. We'd have put that in brackets, put a number there. Let's try going the other way. What if I give you some word for names, right? If I give you these, could we write out their formulas? And this is really the crux of like what we're trying to get at these next couple of days is you need some practice on this. Just like my daughter when she's learning how to read, this becomes more challenging, right? Like we're definitely adding new layers to our tower. So although I'm going to give you guys some brief examples here today in class, I really need to encourage you guys, you need to practice this. Now I've built practice into a few places. There's practice questions in your activity. There's practice questions on your assignment. I even got a slide at the end of these notes that's got practice questions. Okay? But you definitely don't want to just like hear this once and go like, okay, yeah, I think I got it. You need to try it. So anyways, let's give these ones a try. calcium. Here's what I would do. I would write out that calcium is Ca, and it's got a +2 charge. And carbonate, if you remember, carbonate was CO3, and it has a -2 charge. Now, when I want to like fit these together, well, this guy's got a +2, and this whole thing, it's not that the carbon has a charge or the oxygen has a charge. Like, the whole thing has a 2 negative charge. It like fits perfectly. So if I were to write out its formula, it would be 1 Ca and 1 of my CO3s, because they fit. This is calcium carbonate. Anybody know what calcium carbonate is used in, out of curiosity? Fair enough. Calcium carbonate is the main ingredient in chalk, like on the chalkboard. Anyways, let's try another one. Beryllium and hydroxide. So it's going to take a second to find some of these. What is beryllium's charge? Beryllium is Be, by the way. +2. Just give you a second to catch up in case you're trying to find that yourself. Beryllium is +2. So I'm going to even draw this out already right here with a +2. Okay, now we need to figure out what a hydroxide is. And if you're not familiar with it, and you're like, what is a hydroxide? Look in that little table at the top there, right? Just scan through it. It's alphabetical. But what is it? What's its formula, though? You read it as -1. I agree with that. But what is the hydroxide's formula? OH, yeah. So it's OH with a -1. So it's an oxygen-hydrogen. Well, I know there's 2 different elements here, but each of them has a negative charge. So in order for this to fit, I need 1 of these berylliums, and these OHs, I need 2 of them. So here's not how you write it. Don't write this. You wouldn't say beryllium, you need 1 of, and OH, you need 2 of. That's wrong for 2 reasons. First reason is we never bother writing a 1. And the second reason is if I just put a 2 outside of this right here, it kind of implies that there's 1 oxygen and 2 hydrogens. But like this whole thing I want 2 of, so I put a bracket around it. That's the proper way of writing it. There's 1 beryllium, and this collective OH right here in brackets, I need 2 of that. That's how you write its formula. So this is where I'm pretty sure this is like, now we've finished Science 9 and we're moving forward, because like this OH that's in brackets here, you might not have seen the brackets thing before. Maybe you have. Okay, let's try one more. Iron with a Roman numeral 3 nitrate. Well, we've already learned what this Roman numeral means, didn't we? Iron has more than 1 charge, right? Iron can either be a 3 or a 2, but now I know which one it is. This is iron with a 3+. So when I even draw it out, it's got 1, 2, 3 positives to it. What in the world is a nitrate? Okay, well, go find it in your table. It's alphabetical. Thank you, yeah. NO3. But more important than that, not that that's not important, we have to know how many charges an NO3 comes with, because they come with different charges. Some have like +1, some has -1, some has -3. I believe this one was -1. They probably didn't even write the -1, it just probably just said minus. You guys able to find that? Okay. So I know this is a big molecule, and it seems kind of weird, but like each of these only contributes 1 negative. So I am going to need to have 3 of them for it to work. Do not do this. Don't say FeNO33, because that makes it look like you have 33 oxygens. I saved a little bit of room here. Put a bracket around it so that all of the NO3, you have 3 of them. And this is known as your iron 3 nitrate. As a brief aside, let's say that I gave you iron 2 nitrate. That would have been FeNO3 twice. Because rather than needing to have 3 of these, you would only need to have 2 of these. But again, this 2 right here does not mean that there's some sort of number sitting right there. This 3 right here does not mean there's some sort of number sitting right there. A lot of kids, they get confused on that. Okay, so I've done some examples. in my learning cycle, I like to talk about the whole buy-in, knowledge, application. Now I need you guys to try it. Okay, so I've given you some to work on, or I've given you some examples to work with. Now I want to give you guys some time. Okay, so here's what I want to do. For the next 10 to 20 minutes here, depending on how long this takes us as a group, I'll throw on some music to work on in the background. I want you guys to try some of these. Okay, and I think I did the same thing with you guys last day. Over time, I think I'll throw some of the answers up on the board. But if you are stuck or you're lost, can you call me over and I'll work with you guys in small groups. If you feel like you have the hang of it, now you need your practice. Does that make sense? Okay. So I think that's my last slide in our notes. Why don't I throw the radio on for a few minutes, and slowly over time, I will throw the answers up here on the board. Okay. Try this. Work with a group, work with a partner, or call me over. Sound good?